All right, hello. This presentation is on percent error. And so to kind of set the stage a little bit, let's assume that we are a chemist, or let's just assume that we're students and we are taking measurements. You know, for instance, you did a simple lab with measuring tools. So here we are, we're taking measurements and we have a question. And the question is, how close was I? In other words, we want to know, perhaps, how close we really were to the real measurement or to the measurement that would be a generally accepted measurement. So, like for instance, the boiling point of water in degrees Celsius would be 100.0 degrees Celsius. So how close were we to that, you know, hitting the bullseye, so to speak? All right, so we can figure that out. We can calculate something called percent error, and that is something that we are going to discuss in this presentation. All right, now the question might be, or it might kind of lead you to a question, well, you know, how close should I be? Well, okay. Once again, I want us to continually be thinking about the idea of precision and accuracy and the, you know, how close should I be? Well, you know, if we had some, you know, really top-of-the-line, state-of-the-art precision instruments, then that's probably a different discussion than, say, you know, a beaker that isn't really terribly precise. So really, you know, part of this answer is probably going to be tied to the precision capabilities of the tools that we have available or at our disposal. So, you know, there are probably going to be accepted errors that might vary depending upon the precision level of the tool that you're using, okay? All right, something to kind of think about. If you go back to the arrows, you know, compound guys, and I know there might be some traditional guys who wouldn't like to hear me say this, but compound guys that can hit a penny with almost every shot at 20 yards is a little bit different than a guy just shooting a stick and a string, okay? All right, so here we go. We're going to evaluate accuracy and precision, or we can evaluate accuracy and precision. So the first slide here, evaluating precision would require comparing your measurements to your repeated measurements. All right, so once again, we're talking about you taking measurements. So, you know, my analogy was I went out one day and I was shooting, but I was literally aiming right there. But look at all of my arrows. Basically, my fletchings were touching. Was I precise? And the answer is yes, Mr. Day. You showed a great level of precision, but your accuracy could have been just a little bit better, okay? Because we can be precise in our measuring without being totally accurate. So in other words, we might be a little off, but yet we continue to get that same measurement. So that is precise, yet not totally accurate because we're not getting what is the accepted value, okay? Now, however, there's kind of two sides to that coin. You know, what do we want from our tools? Well, we would obviously like to have tools that are both precise and accurate, because it only stands to reason, I think, intuitively, that the more precise our tool, then obviously, you know, we should have a higher level of accuracy. You know, once again, it's going to be hard for anybody to be precise using this tool because you're falling between these two lines and you just end up guesstimating. So if I'm measuring volume and I want to know 250, if I want to go right exactly to that line, then I suppose, you know, that is a fairly, I would think, reasonable level of precision. But if I want to be, you know, if I want to measure volume in a more precise way, especially smaller volumes. Of course, here we go. This is measuring in 1 milliliter increments. So perhaps this is a little more precise. But in measuring, we can be precise without being accurate. But in our measurement tools, we're striving to get both precision and accuracy. All right. Evaluating accuracy, on the other hand, though, requires comparing our measured value to the actual value. So in other words, what you measured versus what it should be. So if the boiling point of water should be 100.0 degrees Celsius, is that the measurement that you obtained? how accurate were you? So you compare your measurement to what it should have been, okay? Precision is when you kind of compare your repeated measurements to one another, all right? All right, so this leads us to some basic terminology that are going to help us for the rest of our time, and then we're going to do a couple of sample problems. So the terminology is, the first term that you really kind of need to get in your mind here is accepted value. The correct value based on reliable references. And as I keep saying, and maybe I shouldn't keep using the same example, but for example, the boiling point of water, and I should have 0.0 here. It would be 100.0 degrees Celsius, okay? That would be an accepted value, okay? Well, what's the experimental value? Well, the experimental value is the value that is obtained from the lab measurement work. Whether that be you, whether that be some scientist somewhere, it is the value that is obtained, okay? All right, and then there's one last term that I think is going to be very, very important to us as we work through these problems here in a minute, and that is the term absolute value. And what I want you to hear about absolute value is it is the magnitude of a real number without regard to its sign. So in other words, here it is. I don't care if it's a positive value. I don't care if it's a negative value. I'm simply going to look at the magnitude of that value without a sign. So in other words, if I had a negative 2.5, I'm simply going to look at 2.5. If I have a positive 2.5, I'm simply going to look at 2.5. Now, the reason you need to know that, kind of a spoiler here, kind of getting the cart ahead of the horse, but your error, when you make an error on a measurement, you could be a little heavy or you could be a little light, so to speak. So you determine that the boiling point of water is 101, well, then you're a little heavy, right? Well, what if you determined it was 99? Then in a sense, you're a little light. And I think you understand what I mean. You realize I'm really not measuring weight. My measurement's a little bit on the plus side, or maybe my measurement's a little bit on the minus side. So let's think about that. But an absolute value is going to disregard that sign, okay? All right, now let's get into the nuts and bolts of this. We can calculate how close we got to the accepted value when we find the error, and then after we find the error, we're going to find the percent error, okay? So think about this before we even get started. What would you think an acceptable percent error would be? How much are you really willing to concede to someone? How much are you willing to let them be wrong? And, you know, depending upon what kind of job you have, and depending upon what you do, and depending upon who you work for, and depending upon the tolerances that you need, you may not be able to allow much percent error, okay? All right, let's continue. So how do I calculate error? Well, it's very, very simple. You simply take your experimental value, remember you obtained that, minus the accepted value. Now this is where I think you could see if your value is lower than this value, then you're going to get a negative number. If your value is greater than this value, then you're going to get a positive number. So your error could be positive or it could be negative, but if you kind of think about that, it makes sense, you know, as to whether you're kind of over or whether you're kind of under, okay? All right, so error. Now, your answer can, once again, be either a negative or a positive value. So positive, whatever you measured, you're a little over. Negative, you're a little under. I mean, that's kind of the way I think about it. Maybe that's not the best vernacular in the world, but that's kind of the way I think about it. All right? All right, so now let's talk about percent error, because really calculating error isn't all that difficult. So we'll calculate error. That's pretty simple. Now, how do you calculate percent error? Well, you take the absolute value, okay, of the error, all right, that subtraction, and you divide it by the accepted value, okay, and then you multiply that by 100. Now, do not make that overcomplicated. Think about what I just said. You're going to take the absolute value of the error, you're going to divide it by the accepted value, and you're going to multiply by 100. In other words, I want to know how close I was to being right, okay? All right, so here we go. All right, let's look at it. Some people, you know, I think work best if they can kind of look at it in a mathematical fraction, you know, equation manner. So you have your percent error, all right, is equal to what? It's equal to your error over your accepted value times 100. All right, and so you know what this is going to do. It's just going to move your decimal place. You know what this is? This is a division. So this is it. This is kind of your equation, not super complicated. All right? All right, so let's give a sample problem. So we had the boiling point of water is measured at 99.1 degrees Celsius. Calculate the percent error. Well, so here it is. We know that the accepted value is 100.0 degrees Celsius. So what would we do? We would take our experimental measurement and we would subtract from that the accepted value, okay? And what do we get from that? Well, we get a negative value, right? Because we were a little under, yes? So we have a negative 0.9 degrees Celsius. Now, here it is. That is our error. That is not our percent error. So now what do? We take this value and we just simply plug it into this equation, yeah? So what do? We take our 0.9 because we're taking the absolute value, and we divide it by the accepted value. And then we multiply by 100. So that is our second step. Our first step was to calculate error, okay, simple subtraction. Our second step was simply to do this division and multiply by 100. Notice I have these scribble lines through the degrees Celsius because they're going to cancel out, all right? So what happens next? Well, I simply do my math. When I do the division, I get a 0.009. I no longer have a unit on there because they canceled out. Now I'm going to multiply that by 100%. So I'm simply going to move my decimal place 2 places to the right. I'm going to go 1, 2. So what is my percent error? My percent error is 0.9. Now, I don't know, I don't have enough knowledge to tell you if I worked at Eli Lilly or if I worked in a pharmaceutical company or I don't know what to tell you in terms of what would your accepted percent error be. But I can tell you that in this particular case, your percent error was it was a little less than 1%. So if you ask how close was I, which was sort of the original question that prompted this, how close was I to the bullseye? Well, you had less than 1% error, okay? All right, so whether that's good or bad, I don't know, but that is where this is at, okay? All right, now, easy peasy. However, there's always a part of this, and so here we go. We need to have just a brief discussion in this on sig figs. And so there are a couple of general rules for significant figures, and you're just going to have to buckle down, and you're going to have to read them and learn them. When you multiply or divide, the answer should have the same number of sig figs as the measured value with the least number of sig figs. Okay, so think about that. Maybe you need to read that again. When multiplying or dividing, the answer should have the same number of sig figs as the measured value with the least number of sig figs. Okay, when you add or subtract, the answer should have the same number of sig figs as the least precise measurement used in the calculation. Which once again, as I think you intuitively understand, the least precise measurement is going to have the least amount of sig figs, right? Okay. All right. Now, if there are some things here that you feel like you need to bone up on or whatever, don't forget that on the YouTube channel there's a sig figs 1, a sig figs 2, and a sig figs review available for you to watch as many times as you need to. Okay. All right. So for this particular topic, because it was like, Mr. Day, you were teaching me about error and percent error, and then you kind of turned into sig figs. Well, because they all go hand in hand. When you give your answers in your calculations for percent error, you also have to consider significant figures. So here it is. For this particular topic, percent error, okay, that's what we're talking about. You're going to determine your sig figs as you go. And I'll show you what I mean here in a second. So as you go through the problem, you're going to determine your sig figs. In the division step, and remember, this is a fairly simple equation. So in your division step, consider the numerator and the denominator's significant figures and go with the lowest sig figs. So look at your numerator, look at your denominator, and look at the number of significant figures in each of those, and then go with the lowest number of sig figs. So let's have an example to really bring this all together. All right, so you calculate the mass of an item to be 220 grams, but the accepted value is 235 grams. So obviously you were wrong, but what was your error and what was your percent error? Okay, so far, not complicated. The first step, really easy, because we know what we're going to do. We're going to go step one and we're going to calculate our error. So we're going to take your measurement and we're going to subtract from that the accepted measurement. Now, once again, this is a negative value because unfortunately you undershot the mark just a little bit, right? You shot a little low. So you're going to do your subtraction and you're going to get negative 15 grams, okay? Except you know that at this point, you're going to go with absolute value. So now that you have the error, you're going to go to step two, which is you're simply going to plug it in. You're simply going to plug it in, and you know that you're going to have your error, okay, 15 grams, over what the answer should have been, yeah, or what the accepted value is. I can't say that that's necessarily what it should have been. You might not have had a very precise tool. All right, your grams are going to cancel out. Now, here's where we took the turn, and now you're going to stop, and you're going to say, okay, I want to look at my significant figures, and you're going to say, okay, 15 has 2 sig figs. So what are you going to do? You're going to acknowledge that, because that's going to play a part in your final answer. So what are you going to do now? You're simply going to do the math. You're going to divide 15 by 235, and then you're going to multiply by 100. But remember, I said we were going to do significant figures as we go. So what are you going to do? Well, it's simple. You're going to divide these two numbers, and your calculator is going to spit out something that looks like this. And you're going to look at this value, and then you're going to look here, and you're going to say, oh, my lowest amount of sig figs was 2. So I need for this to have 2 significant figures. So we know by our sig fig rules that these zeros are not significant. So we are going to allow this, where these are going to be the 2 numbers we're going to take. I think you understand that. We're going to allow this 8 to round this 3 up. So we're going to have 0.064. So this is how we got this from this, okay? Because we considered this. And how did we get this? Well, we got that from this, okay? So we do our subtraction and get our error. We plug in our error. We do our math. We look at our number of sig figs while we're doing the math. We get our answer on our calculator for this step. And we simply round this to 4 so that we now have 2 sig figs. We multiply by 100, which moves our decimal place 2 places to the right, and we get 6.4%. So what was our error in this particular problem? Our percent error was 6.4%. So, one more time. You got a value of 220, accepted value was 235. So what are you thinking? You're thinking, okay, I need to calculate my error. That's easy, Mr. Day. Yes, it is. I'm going to do a simple subtraction. I'm going to get a negative 15. Except, Mr. Day, I'm going to go with the absolute value for the next step. Fine. So we're going to drop off the negative. All right, so we drop off the negative and we have 15 grams over 235 grams. Why? Because that's our error over the accepted value. We're ready to do some math here. Okay, that's a simple division. But before we do the simple division, we're going to consider, as we go, we're going to consider our significant figures. So we have 2 here. We identify that. We go ahead and do this math on the calculator, and this is the answer that we get. We take this and we round the 3 to a 4. We now have our 2 sig figs. We multiply by 100 and we get 6.4%. Easy peasy, we got the answer. This was the percent error that we had on this particular measurement. What caused it? I don't know. Why did it happen? I don't know. I mean, what's acceptable? Yeah, I don't know. Would a 6.4% error sound good to you? Probably not. And but as we know, our ability to be accurate is also going to be tied not only to technique and knowledge, but it's going to be tied to the precision of our tools. So there you go, percent error.